Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on relative motion analysis. When you look at the relative motion approach, you really expand the scope of solving more class of problems. Absolute motion analysis is restricted, whereas relative motion analysis helps you to solve a larger class of problems. And one of the key points we learned in the last class was what constitutes general plane motion. Here I have the body experiencing general plane motion. This motion can be thought of as a combination of rotation and a translation. So, I rotate this first, it is deviating from the path, and I give a translation. This comes to the path as what we have seen in this diagram. So, it is a very important concept. General plane motion is a composition of a rotation and a translation. It is a very subtle concept. And when I want to view the point A sitting at B, that means I have attached a non-rotating translating axis at B. The axis can have velocity as well as acceleration. It is not an inertial frame of reference. And when I have a rigid body, this distance remains fixed. The relative linear velocity is perpendicular to this line joining these 2 points, and the body the point A, when I view it from point B, it rotates. Observe the sense of rotation. Now, what we would see is, we would fix the axis at point A and view point B. Here again, if you look at the sense of rotation, it is one and the same. This is by virtue that you have been able to appreciate general plane motion consists of a rotation and a translation. Now, we are translating with the body. When I view it from different points, the mathematical details will differ, but the sense of rotation still remains the same. This is what is illustrated. It says that the sense is same for both the points. The idea of attaching a translating axis at B amounts to translating with velocity Vb, and you have a corresponding rotation here. If I attach the axis at A, it amounts to travelling with velocity Va and rotation in this way. We will go and solve a very practical problem. You have a reciprocating engine. This is again a example of 4-bar mechanism, and it is called a slider crank mechanism, and the crank OB, this is the crank OB, revolves in a clockwise direction at the rate of 1500 revolutions per minute. First, identify the nature of motion of the crank, piston and the connecting rod. And you have to determine certain quantities at a particular crank position. The crank position is given as theta equal to 60 degrees. you have to determine the velocity and acceleration of the piston A. When you start solving the problem, we have developed the equations based on two arbitrary points A and B. To make your life simple, more or less these points are similar to what we have started with. So, you do not have confusion on interpreting the equations first. Once you get the grip of the equations, we can label it in any way and solve the problem. And you are also asked to determine the velocity of the centroid of labeled as point G. Solve it by sketching the velocity and acceleration polygons and also by vector analysis. See, the idea is, if you draw the velocity and acceleration diagrams, you get a better physical appreciation of the problem. On the other hand, when you get into vectorial analysis, it becomes totally mathematical. In a sense, it also will be slightly boring to do that. Let us understand the motion of this. So, this is how the whole system operates. Now, we will go and individually analyze what happens to the crank, what happens to the connecting rod, and what happens to the piston. The connecting rod has, the crank has a fixed axis rotation, and your piston has a reciprocating motion, and the connecting rod has a general plane motion. That is what you have to recognize. It is a very nice problem where you have the motion of all three varieties in one problem. And what is given in the problem statement? The angular velocity of the crank is given in revolutions per minute. It is desirable that you convert it into radians per second. So, when you do that, I get that as 157.08 radians per second. See, you have to interpret the engineering quantities properly. You should not ignore that conversion you have forgotten, you have overstepped that, all that you should not say. You should handle all these quantities with right units. And we have already noted that crank OB is under fixed axis rotation. So, I have a fixed axis rotation like this. The velocity at point B can be determined directly from that. When I have a fixed axis rotation, the calculations are very, very simple. This is what I told you earlier. Though we say fixed axis rotation, we have a mental block in looking at axis of rotation. Even when I have a non-rotating translating axis attached, I still invoke fixed axis rotation equation when I want to look at what happens to general plane motion. Before that, since we are analyzing a crank which is having a fixed axis rotation, you can write the quantities. Vb is nothing but r omega, and I get Vb as, when I do the computation. I would also appreciate that you check these calculations using your calculator. This comes to be 15.71 meters per second. And we also know what is the direction of Vb. It has to be perpendicular to this crank. So, that is what is indicated here. I have Vb is perpendicular to this. I have this as 15.71 meters per second. And what we have determined? We have determined the absolute velocity of point B. And if you look at the connecting rod, point B is also part of the connecting rod. But for the point B, we have already determined the absolute velocity. So, I can attach a translating axis to point B and look at what happens at point A. taking B as a reference point, I can find out the velocity of A. We have already looked at that this is experiencing general plane motion. If I attach a non-rotating translating axis at B, what way I would perceive A? It would simply have a circular motion with respect to B. So, the velocity of A is equal to Vb plus B relative velocity of V with respect to B, velocity of A with respect to B. And by virtue of the piston having a reciprocatory motion in this slot, I can say that this is the velocity of A. We have already determined what is velocity of B. So, these are known. And can you comment about what is the direction of velocity of A with respect to B? You can do that from your general plane motion analysis. We may not know the magnitude to start with, but we are in a position to find out its direction. The velocity direction would be perpendicular to the line joining B and A, because I would perceive by sitting at B on a non-rotating translating axis, the point A would have circular motion. And I think VAB is perpendicular to the line AB. And for us to proceed further, I need to have certain geometric quantities. I need to know what is the angle beta when theta equal to 60 degrees. I am doing all these calculations systematically, because when you have to solve a practical problem, you have to bring back your old memories. You have learnt about properties of triangle, sine rule, properties of circle, all that you have learnt in your 11th and 12th standard, you cannot forget. You must bring back those memories. And I can get this from the law of sines. I can write 100 by sine beta equal to 280 by sine 60 degrees. And this gives the value of beta as sine inverse 0.3093, that finally gives you this as 18 degrees. So, I know how to put the direction of the relative velocity of A with respect to B. This is the key aspect that you have to recognize. This is what we have spent time in understanding general plane motion, which can be thought of as composition of a rotation and a translation. When I attach a translating axis, I perceive only the rotation. So, I put the velocities, I have Vb, I have Va, and I have to put Vab perpendicular to this, and one can also guess which should be the direction of velocity of A with respect to B, because it has to close the polygon. Fine. I am essentially finding out what is Va. I know what is the direction of Vb. So, I can always say that the direction of Va with respect to B should be like this. So, this is what I am going to have. I have this perpendicular to this line joining B and A, that happens to be the connecting rod, what we have also shown as a line. So, I get this, I close the polygon. Now, I know what is the velocity of A with respect to B. And we will look at the magnitudes. I need some more angles for me to proceed. So, I need to get that by the appropriate properties. and we have already said that this is perpendicular to the line joining this, and this line is at angle 18 degrees from the horizontal. So, from the vertical this is about 18 degrees. So, if I want to find out this angle, that turns out to be 72 degrees. And this naturally comes to be 78. And from the trigonometry of the velocity triangle, the values of VA and VA with respect to B are determined as follows. I have VA by sin 78 equal to 15.71 by sin 72. I get VA as 16.16 meters per second. Similarly, I can also write for VAB, velocity of A with respect to B divided by sin 30 equal to 15.71 divided by sin 72. So, I get the velocity of A with respect to B as 8.26 meters per second. Is the idea clear? Can you find out with these quantities what is the angular velocity of the connecting rod? You can do that. Fine. So, that is what we are going to do, angular velocity of AB, that is simply VAB divided by AB, that turns out to be 29.5 radians per second. So, let us look at the connecting rod, and we have attached our non-rotating translating axis at B. So, it is shown as fixed, and I have perceived the velocity of A with respect to B like this. We are also asked the question, what is the velocity of point G? And from this diagram you can easily say what is the relative velocity of G with respect to B. And before that, we are also looking at from the sense of VAB, I attach the angular velocity direction and I say that it has to be counterclockwise. All this is very important. You have to physically appreciate all aspects of the problem, and whenever you make a statement, there has to be a mathematical basis for it, and it should fit with the physical reality. So, I have determined this angular velocity direction, and we will have to find out velocity of G, fairly simple, and Vg can be written as Vb plus velocity of G with respect to B, and we have already looked at velocity of A with respect to B, and we can say about what should be the relative velocity of velocity of G with respect to B. I can simply put this as Gb into omega AB, which could be rewritten in this fashion. And when I do this, I get the value of velocity of G with respect to B as 2.36 meters per second. And it can be easily drawn in this sketch as a line like this. These two are parallel, because I see the whole connecting rod rotates with respect to point B. Once you know the relative velocity, you already know what is Vb. I can find out easily what is Vg. There is no great big deal in getting that. That is what is done in the next slide. We already have the direction of Vb. I would like you to make neat sketches. You have to be trained as engineers to draw neat sketches. And what I have done also needs sketches. I have not taken any geometric assistance to draw them. These are freely drawn figures only. So, I have velocity of Vb and we know velocity of g with respect to b, which we have seen in the previous sketch. It is in this direction. It is perpendicular to this connecting rod. I have velocity of g with respect to b. When I close the vector polygon, I get the velocity of g, and that is what is shown there in the actual point. We can also determine the magnitude now. For that, again I need to do properties of the whole diagram. So, I need to find, we already know the angle is 72 degrees, and I can write from knowledge of trigonometry cos 72 degrees as a function like this. So, you have to go back and brush up your basic trigonometry, properties of triangles, properties of circles. So, I can find out from this the quantity Vg. Vg turns out to be 15.4 meters per second. Please verify my calculation using your calculator. The idea of solving this problem systematically is to bring about, you cannot come and say I have forgotten the sine rule, only a sine rule I have forgotten, all that you should not say. For solving a practical problem, your old knowledge is required. Fine. So, brush up those fundamentals. Now, let us move on to acceleration analysis. We have already recognized that connecting rod undergoes general plane motion. Points A and B are now visualized as points on the connecting rod. Again, the statement is emphasized, for a non-rotating translating axis attached to point B, one would visualize point A to have circular motion with respect to B. See, the next chapter, we are going to have an axis which will be rotating with the system. So, when I say non-rotating translating axis, you should appreciate in that context. We are making a very clear distinction. In one class of problems, you simply attach a translating axis. In another class of problems, your life becomes much simpler if you attach a rotating axis. So, I can write the expression for the acceleration at point A as AB plus the normal component of acceleration, normal component of acceleration. These two quantities are essentially relative acceleration quantities. And what all things that you know about A, acceleration at A, you can definitely say that it will be horizontal direction. Fine. And about B, you can find out everything because it is part of the crank. So, I can find out what is the absolute acceleration of point B. Once you know omega, which we have already determined, I can find out AAB. The only catch is I have to find out alpha A, AB. That is what I have to find out. Okay. And when you go to point B, it is said that this crank rotates with a constant angular velocity. So, I have only a normal component of acceleration, there is no tangential component, and I can write this as r omega squared. So, the absolute acceleration of point B turns out to be this magnitude. I have got this as 2467.41 meters per second square. See, again and again you use the circular motion equations intelligently. You have to appreciate general plane motion is a composition of translation and rotation, and put an appropriate axis and then calculate all these quantities. Do not apply Newton's law in any one of these coordinate system. We are determining the absolute acceleration of point A by using this intermediary. Once I get the absolute acceleration, in that frame of reference apply the Newton's law. That we have to do when I go to kinetics. We have already seen that connecting dot undergoes general plane motion. We have already determined the angular velocity, that is omega AB is 29.5 radians per second. So, I can find out the normal component of relative acceleration easily. There is nothing but RAB into omega squared AB. So, I get this value as 243.67 meters per second squared. As I told you earlier, one needs to find the angular acceleration of the connecting rod to calculate the tangential component of relative acceleration. So, we will take advantage of the acceleration diagram and let us look at what all quantities that we know. Direction of AA is horizontal, that I have already told you, because it is reciprocating like this. So, I can put this as a horizontal line, and we know the absolute acceleration of point B. So, AB is known and the relative acceleration of the normal component is also known. Normal component is known like this, and your tangential component will be on this direction. Okay. So, I have drawn this AB because AB I know completely from the problem statement, and this direction is known. So, I can also put that. See, these animations are carefully done so that you have sufficient time to write it down. It is done slowly, and also the sequence is done in such a manner, even if I do not speak, when you see the animation, the logical evolution of concepts you can appreciate. All this take a very long time to do the animations, they are not very simple to do, time consuming. Lot of effort has gone into all this. Line of action of the tangential acceleration is known. As of now, I have no knowledge what is the sign of acceleration. I have determined the sign of angular velocity from the physics of the problem. Knowing angular velocity does not tell you anything about the direction of acceleration. This is the point I want to drive home. Fine. Let us see what way the acceleration turn out to be in this problem. But I know this direction, so I can complete the polygon like this. So, I will have this in this. From this polygon, I am also in a position to find out what is the final direction of this. So, we will continue with this in the next slide. So, the question what I have raised is whether it is clockwise or anti-clockwise. That question is unanswered at this stage. So, I have this from the acceleration polygon equating horizontal and vertical components. I can do this AA is so much, and I am in a position to calculate the tangential component, that turns out to be 2167.63 meters per second square. And we already know what is the velocity of, what is the acceleration of A, 795.61 meters per second square. And so, the acceleration of A is marked. So, this fixes the direction of the tangential component of acceleration. Once I know the tangential component of acceleration, the direction of alpha can be fixed. So, alpha AB is nothing but AAB tangential component divided by R. That turns out to be 7741.54 radians per second square. So, can you tell me what is the direction of this acceleration? We know the direction of this with the sense of AAB, the angular acceleration AB related to B can be determined. So, I get this as clockwise. See this problem, it is very interesting, that is why I chose this problem. With this problem, I am able to bring out all the nuances that you can come across in a generic problem. I have combination of fixed axis rotation, translation and a general plane motion. And once I know the angular velocity, you should not jump to saying angular acceleration in the same direction. These are all the common mistakes students do. When you know one quantity, as a scientist, without assessing what is the other quantity, don't jump to easy conclusions. Fine. Now, let us again solve this problem through vector analysis. So, we will take origin as at point O. I have put the positive x axis like this, positive y axis like this, all the other quantities are put, and you have to find out the position vectors very carefully with respect to this coordinate system, whatever the coordinate system that you take. And we have already determined this, the angle beta from the previous analysis. So, the position vector of point B you can find out and write very easily, that is nothing but minus 0.1 cos 60 degree I plus 0.1 sin 60 j. When you simplify, it takes a value like this. All these position vectors you should do it very carefully with reference to the coordinate system that you have taken. What is the velocity at B? It is nothing but omega cross RB. Omega we have already determined, RB we know, so I can calculate what is VB. It is a simple mathematical operation. So, I have this, and to aid your cross product, I have also put this ijk like this, so that you keep track of the signs properly. So, finally, I get VB as 7.85 j plus 14.14 I meters per second. See, mind you, you would find small variation in values when you do a vectorial analysis, primarily because when you are determining the position vectors, you are not taking all the digits. Fine, the round of errors can come. So, that is very common. You should also know in any engineering calculation, you should take care of round of errors. There may be small deviations from the numbers which you have got earlier. So, you have to keep track of. So, when you are using this, I have actually rounded off to 2 digits. If I round it off to 3 digits, maybe I will have improved estimations. Fine. So, that matters. Whenever I put this vectorial calculation, whether I stop at 2 digits or 3 digits, it matters. So, the VB turns out to be 16.17 meters per second. I think earlier we got it as 16.16. So, there will be some deviations. Okay. We have determined what is the velocity of point B, and velocity of A can be obtained from relative velocity equation. The equation is like this: V A equal to V B plus V A with respect to B, and velocity of A related to B is given by, we know from attaching the axis here, if I know the angular velocity, I can calculate that. So, I put that as omega A B cross R A B. And we have R A B, write it with respect to the reference axis. It is written in this fashion. And when I find out the velocity at A, we know that this is translating. So, the direction is known, the direction is I do not know the magnitude V A. So, I write the expression, then you collect terms involving I, terms involving j. This is how you do simplification in your vectorial analysis. So, I write the expressions. So, I write V A I equal to 14.14 I plus 7.85 j plus omega A B k cross the position vector minus 0.27 I minus 0.09 j. So, on grouping j terms together, I get the value of omega A B, that is 29.07 radians per second, and this is I have this as k. So, this is counterclockwise. In a vectorial analysis, the directions are determined from your mathematics itself, straightforward. And on grouping I terms together, I am in a position to get the velocity A. I get velocity A equal to 14.14 plus 0.09 omega A. We have already determined omega A B. On substitution, I get the value as 16.77 meters per second. See, in a vectorial analysis, you have to carefully write the position vectors and also the appropriate angular velocity, and write the equation and group the I terms, j terms, and once in a while you may probably peep in and see whether physically these numbers are all right, directions are all right. On the other hand, when you do a vector polygon, when you are writing the velocity polygon, you have to visualize, and that aids your thinking, and you can also appreciate the physics of the problem better, and you become a better engineer. So, in the initial stages, you try to visualize as much as possible. Also learn the trick of doing a vectorial analysis, and vectorial analysis to an extent dry. Okay. Having said that, when I go to rotating axis, I would completely dwell on vectorial analysis, because that becomes simpler to handle with. Whenever there is an opportunity to visualize, better visualize. That will help you to think better. And like we have determined the velocity A, we will also determine the velocity G. Write again the relative velocity equation. You are able to write this relative velocity equation on the strength of understanding general plane motion. We have attached a non-rotating translating axis at B. So, we are in a position to write this relative velocity equation, otherwise it is not possible to write. So, VGB is omega AB cross RGB, and when you substitute these quantities in the relative velocity equation, I also get the final values, and we need to get the position vector of point G. So, that is written in this fashion. So, RGB is minus 0.08 I minus 0.02 J. if you do not handle this quantities properly with appropriate number of digits, there would be variation in your numbers because of round off errors, and all engineers have to appreciate round off errors in major calculations. So, you have to accommodate your design to take care of such errors in your analysis. So, I have the expression for Vg. We have already determined what is omega AB. So, I have substituted that, and to aid your thinking, Ijk is put like this. So, I get Vg as 5.52j plus 14.72i, and you will also find out the magnitude. The magnitude turns out to be 15.72 meters per second. And I have to find out the acceleration. Again, you write the relative velocity expression. Instead of doing it from a polygon of the acceleration, we are directly handling the vectorial quantities here. Even for that, I started with this equation and then wrote down the polygon. And the normal component is omega cross r. We are finding out what is the relative acceleration A with respect to B. So, I put the appropriate omega. These are all the places where you can make mistake. If you do not keep track of your omega properly, you may use omega of the crank to this place. On all your calculations will go for a 6. Okay. So, handle the mathematics also systematically. And I have the tangential component as alpha cross RAB. And this is again brought to your attention. The point B has only normal component of acceleration. So, I can write the normal component like this, omega OB cross RB. So, that turns out to be, we have already learned the trick. If I have a vector triple product, how do I write the final quantity? You do not have to go through the conventional approach, directly write the numbers, and the vector is same as this, but with the opposite sign. So, you can take advantage of all this, fine, because you are going to do this repeatedly. There is no point in doing this in stages and finally arrive at this vectorial representation. And I can also find out the magnitude. The magnitude is 2540.36 meters per second square. Then I move on to determining the other quantities. So, I have this normal component of acceleration is like this. Here again use the simplification which we have learnt earlier for the vector triple product and find out the value as 228.17i plus 76.06j. And the tangential component of acceleration is alpha cross RAB. So, I have this expression. I do not know the value of alpha AB, okay, and I will write the complete expression. And from this, by grouping the terms, I am in a position to calculate what is the value of acceleration at A as well as the angular acceleration of the connecting rod. So, grouping the I and j terms, I get one expression like this. I have another equation. I have two unknowns and I have two simultaneous equations, and it is possible for me to find out the values. So, alpha AB turns out to be minus 7943 radians per second square. So, this directly tells me that this is clockwise, and I can also find out what is the acceleration of point A. The idea of solving the problem by both graphical approach as well as a vectorial approach is to appreciate what are the aspects you should pay in your graphical approach, what are the aspects that you should pay in your vectorial approach. And in your exam problem, I may specify the method. I want you to be proficient in both of these methods. So, in this class, we have taken up a very interesting problem dealing with slider crank mechanism. It is very widely used in many applications. From the data given in the problem, you have been able to find out what is the acceleration of the piston and also the rotation of the connecting rod. And we recognize the connecting rod has a general plane motion. And we also have to appreciate by attaching a non-rotating translating axis to a rigid body, you see other points in the rigid body having a circular motion with respect to the attached axis. Thank you.